Okay. So last time in class we introduced Coulomb's Law, which is described by the equation V equals K Q1 Q2 divided by D. The V represents that potential energy. And we talked last time about how that value can be positive or negative. And whether it's going to be positive or negative is going to determine whether it's an attraction or repulsion. If it was a negative value, it's going to be an attraction. If it's a positive value, it's going to be a repulsion. We also talked about how we looked at numbers and how we use the numbers here with this, which is a little bit different because we're going through and use, we say a large attraction, but on a number line that would be a really small number. So we look at the magnitude and the sign. So the magnitude is going to tell us how strong something is, how big is it. The sign is simply telling us, is it an attraction or is it a repulsion? Does anybody have any questions? Now, for the most part, we are going to treat Q1 as if it were an electron. That's not always the case, but for most of our discussion today, Q1 we'll treat as just a -1 value representing the electron that we'll be looking at. Q2 will be the positive charge from a nucleus. D, that's going to be always a positive value. Remember we said that. And K is always going to be a positive value. For today's discussion, to make the math easy, we're just going to treat K as if it were +1. Remember, it's like the last bullet on that slide says, we'll rarely use this equation to actually solve a numerical value. We use this equation mainly to show the relationships. How much bigger or how much smaller? Is something going to go up? Is it going to go down? Is the attraction going to be smaller or is it going to be greater? Questions? Ella?
So on our little quiz next week, do you know about like what's going to be on there? How far?
You mean Friday?
Yeah, the next coming class.
Basic fundamental stuff like we're talking about in class. Okay? I mean, I'm going to expect you to be able to use that equation to at least make predictions or comparisons. Understanding that negative is attraction, positive is repulsion. If you understand how the trends that we're talking about, when I say trends or the comparisons that we're going to make in class, you're good. Okay? I'll also take the opportunity here to re-emphasize that if you've got questions you really need to ask. If you're not quite sure about something, please ask. The reason why I'm taking the time that I'm doing here is because doing it up front makes stuff later go much quicker and makes it easy. Okay? Questions before I go on? Okay. I think that's about all I wanted to do on that. We finished this one off, right? Yeah. So last part of class, we looked at these 3 atoms. And we saw that we're looking at 1 proton, 1 electron. I know it doesn't say it, but this is a hydrogen atom. It's giving us distances, like atom letter L there is 1,000 picometers distance. So that's the distance between the proton and the electron. For the Atom Q, we decreased that the distance to 500, and then atom T, we decreased it down to 200. The key to this, and the reason why we're making these comparisons, is the next slide where we had the distances, we had the ionization energy, and we had the potential energy. And the importance here of these was that potential energy tells us how strongly the two particles are attracted to each other. So the column V, they're all negative because they represent an attraction. Because you got a positive and negative with each other. And opposites attract. Mathematically, it has to be negative. K is positive value. Electrons negative, protons positive. So we've got opposites. And D is a positive value. So if you plugged in all those variables, you would have only one negative value up there. And since it's multiplication and division, your answer has to come out to be negative. We see that if we go down, the distances get smaller. And as a result of that, the potential energy gets technically smaller, but if we read it as the negative sign means an attraction, and the magnitude is the size, the attraction as we get closer together is getting larger. So when you have atom E that has a potential of negative 4.62 times 10 to the negative 20th, yes, I understand it's a really, really tiny little decimal number, but when you go to compare that with atom Q, which is 500 picometers, we get the negative 4.62, but it's times 10 to the negative 19. That value, the magnitude of that, is larger. 10 to the negative 20th versus 10 to the negative 19th. 10 to the negative 19th is a larger numerical value. Magnitude. And it's negative, so it means an attraction. Which makes sense. Because if you decrease the distance between particles, what's that going to do to the attraction? Go up. You have little magnets on the flaps, right? Play with that for a second. Try to get that magnet as close to being closed as possible without closing all the way. You don't have your iPad, Kristen?
Oh, don't get it.
No, that's just lazy.
Tuesday.
What happens as it gets closer, people? It gets stronger. All right, let it close all the way, and then do this. Pull up on it, but don't pull up on it strong enough to lift it up. Do you have? You can exert a certain amount of force there, right? And still not have to have it pulled up. If you pull up enough, now you're going to be able to detach it. That's just like the ionization energy. If I want to remove the electron from an atom, I need to put energy into it. How much? Equal to the amount of the attraction. And that's why in this table here, the IE, the ionization energy, is positive. But the number is the same. The magnitude is the same. Because at the V, the potential energy is representing the attraction, and we've got to remove the electron, we need to add energy to counteract that or break that attraction. The amount of energy we have to add has to be equal to what that attraction is. That's why they're equal but opposite in their sign. Questions? Okay. So let's start application. I'm going to call, hold on, I want to lock this. I'm going to call this A and this B. Okay? Which of the following systems will have the larger ionization energy? Meaning, which one will be harder to remove the electron from? Why? Closer to the nucleus. So this is going to be the answer, because if you look at the map, what happens to the V, the value for magnitude of V, if D increases? Say again? It decreases. So if you increase the distance, you're going to decrease the attraction. Now between A and B, the only thing that's changing then is the distance. Because you have an electron attracted to a +2 in both instances. In a sense, your numerator is the same for both of them. You have, for A, you've got V equals, remember we said we're going to use +1 for K, right? -1 is the electron, +2 for the distance. Sorry, for the nucleus, +2. And then for the distance down here, I got 500. V would equal -2 500ths, or -1/250. Somebody get out a calculator and do that math for me, because I can't. No, that's a 0.0025. It's a quarter. No, I can't do the math in my head. I should be able to, but I can't.
1 divided by 250?
Yeah.
It's 0.004.
Okay, if I do B, then I'm going to have +1 times -1 times +2. That doesn't change. Numerator is the same on both of them. This is going to be divided by 700. So V is going to equal -2 700ths, which is equal to -1 350ths, or V is equal to what? What's 1 divided by 350? 3/8? 2/8. I'll just leave it at 2/8 because it gets the point across. Which of those two values is bigger? Magnitude. 0.004, 0.0028. That's the stronger attraction. Everybody good? Does anybody have any questions?
Wait, which one's the strong one?
The 0.004?
Okay.
Okay. We'll call this A, we'll call this B, and this is our explanation. Take a second, read it. Think about it. Don't blurt out the answer. Everybody has an answer ready, right? Because now I'm going to pick on somebody randomly. 14. Eli.
It's B, and the attraction of B is 2 times larger than
Say it again?
A. It's, I think B has the greater ionization energy
And what was the explanation?
because the numerator, like if you worked out the equation for A, the numerator you divide it by 2. And if you worked out it for B, you're just dividing by 2.
Okay, you're upside down. I'm going to have you read me the numbers. So I'm going to have I'm going to make this color coded. I'm going to have A be red and B be blue. So I'm going to put +1 for K. What's the charge for the electron?
-1.
And the nucleus, they say, is what?
+2.
+2. Now, I'll only put D1 down here. Okay? Because they say distance at D1. Because I think you chose the wrong one for the right reason. Wait a minute. You have the right reason, but you've got the wrong one chosen. So I'm going to change color. So V for B, what changes up on top?
The nucleus, the proton is +1.
Okay. Make up a number for D1. What do you want D1 to be equal to?
50.
50? Okay. So if we make D1 equal to 50, and substitute that in, we're going to get, for A, V equal to -2/50, which is 1/25, which is going to be 0.04, I think. B is going to be what? B is going to equal what?
-1/50.
1/50. And that's going to give us -0.02, I believe. So which one? Oh, I forgot my negative sign. Which of those two values there, Eli, is going to be the larger attraction? A. But you said it was going to be what?
B, because it's, yeah, I was mixed.
That's why I said you had the right explanation. It is going to be 2 times larger. But it's going to be A because it's got the larger charge. Everybody okay with that? So up to this question right here, we've pretty much been looking at everything from the distance perspective. Now we've got charge. We're looking at the charge. If you change the charge, you're going to change the attraction. Now I had Eli just choose a distance. It really doesn't matter what the distance is mathematically, because they're saying the attraction for A has to end up being twice the value for B, because the nucleus is twice the charge. Who's got questions?
Didn't you say that, I think it was, like, from negative, the farther away it was, like, the farther away it was, it would have the lesser attraction?
Yes. But in both of these, the distance is 50. At least that's what Eli said.
So, what is V?
V is the potential energy. That's what's telling us what the actual attraction or repulsion is. Okay? That's why, so when I say V is equal to negative 0.04, what that's saying is that the potential energy, based on the numbers that I plugged in, is negative 0.04. Negative is an attraction. That attraction is worth 0.04. For B, the potential energy based on the setup was negative 0.02. Negative meaning it's attraction with a value of 0.02. Now, if that attraction there, the 0.04 magnitude, is larger than the 0.02, that's why the A is going to have the larger attraction. It's going to be the higher ionization energy. So ionization energy and attraction are tied together. The stronger the attraction is, the higher the ionization energy is going to be. Because if the attraction is larger, that means that it's going to have a potential energy that's going to have a larger magnitude. It's just a negative value. Who's got questions? Anybody? Okay. Consider a hydrogen atom and a helium ion, He+1. Helium ion has 1 electron with 2 protons in the nucleus. Which of these do you expect to have the larger ionization energy? Explain your reasoning, including any assumptions you make. I'm going to give you a minute or so here to write some stuff down, give you the opportunity to think about this. And I would strongly encourage you to use that equation to help make this, to help do that explanation. And I'll choose a random number again and have whoever answer that. Alana, it's you.
I'm not sure.
Okay. Then I'm gonna help you walk through it, okay? Pick an element, hydrogen or helium. Helium? Okay. So helium's going to have a charge of +1, so it's only got one electron, all right? So we're going to say V equals. We want to know what's the potential energy, okay? We're going to make K as a +1, just to make the math easy. Charge of the electron. What's charge of proton? Or what's, I should say, what's the positive charge for the helium? Because it's got 2 protons. Is everybody okay with the top part, the numerator? Now, what do we not have given? What? What do we not have given? What? So from this equation up here, what's missing here? D. We don't have a D. So I'm going to put distance of helium. Okay? Now, hydrogen. +1 for the K. -1 for the electron. And +1 for the proton in the nucleus. Correct. And again, what do we not have? We don't have a D. So I'm going to put D hydrogen. Now, mathematically, we could simplify this up and say, for this one, V would equal -1/dH, D hydrogen, okay, for the distance of hydrogen. Okay with that? And for the helium, we could say V is equal to -2/d helium. Now, I know we don't have a number there for D, but what does your gut tell you as to which one would be the stronger attraction? The helium? Why? It's got the larger number. Correct. And I would agree with that. Helium is going to have the larger attraction. But what are we assuming? What are we assuming here? The distance. What are we assuming the distances are? They're approximately equal. I will tell you this, they are not equal, but they're not very different from each other. For helium to have less attraction, your distance would have to be over double the distance of hydrogens. Does that make sense? As your distance goes up, your attraction goes down, right? And we already have, based on just the numerator alone, the attraction between the electron and helium and the electron and hydrogen, for helium it's twice as large because you have 2 protons. To counteract that, you'd have to have the distance be twice as great. And it's not even close to being that. That help? Okay. Questions? You guys are quiet today. I don't know whether that's good or bad. Okay, development of shell model, ionization energy. According to the, oh wait a minute, back up. Did we do this already? Had we done this right here? Had we done this already? Yeah, we have. Yeah, we have. Go look at that one. What's the difference? We just didn't call A helium. We just didn't call B hydrogen. Can we see it now? So this is the thing. Here, in this one we did, it's more hypothetical. In this one, this is more practical. We're actually applying it to real atoms. So these basic concepts, this is why I'm taking it slow here, because if you understand, if you know these basic concepts and how these relationships are, then we can explain the properties of the elements very, very easily. Because the property of the elements, the properties of compounds, all rely on one thing. How are they attracted to each other? Okay? All right, give you about, I don't think you need a minute, but we'll give you a minute here. Look at this. Be ready with an answer. And I will randomly roll again. And be prepared to explain or ask for help. Elizabeth, your number came up. Are you ready with an answer, or you still got a little work to do? So you're writing some stuff still. B, as in boy?
Yeah.
Why?
There's negative and positives that are really attracted to each other.
So there's an attraction. Class, what can it not be? Based on that, because we have a positive and negative, what can it not be? It can't be a positive. It can't be A or D. Mark them out. Now, Elizabeth, why B?
Because they're extremely close.
And the closer you get, what?
The larger the magnitude.
Larger the magnitude or stronger the attraction. Good job. Everybody okay? Does anybody have any questions? Okay. Challenge time. You have 2 electrons and 1 helium. The diagram's down there at the bottom. Helium nucleus. Diagram's down at the bottom. Those 3 particles are arranged in a straight line as shown below. The electron on the left is 300 picometers from the nucleus. The electron on the right is 400 picometers from the nucleus. Plug the values. I know it says do not calculate, but at least set it up. And go ahead and use +1 for the K value. Plug the values into Coulomb's equation for the 3 possible arrangements for the chart. Huh? I'm mirroring it. Right now, I'm going to leave it as is because I didn't have just. I'm hoping this reverse well because period 1 and period 6 both crashed. I'm trying something different. Yeah. Because I've got enough people absent. I got a couple people in quarantine that they want to fall behind.
So are you going to cut this part? Recording right now?
Yep.
Are you going to hear us?
Yep.
Are you going to cut it?
Just too much.
What do you mean?
Just like it's going to hear us.
I don't know. I'm going to cut this out.
Okay, quarantine people.
It's also there for if you guys want to go back and look at it again. I'll have it up.
Do you do that every day?
No, but because enough people have been absent, I'm starting to. All right, we're gonna get 3 people involved here. Not now. 9. Megan. Not yet. I'm just letting you know you're gonna be. I already had 4. 24. Terry, you're going to be one of the people answering. Joey, you're the 3rd. Okay. I think you've had enough time. Magnus, since you were first chosen, pick a combination. Tell me what it is. So I'm going to write it on a specific area here.
So on the left side.
The what?
So on the left side.
Okay.
It says 300 picometers.
So V equals.
Plus 1 times plus 2 times
Over 300? Good. Kateri. What's your choice? Which combination did you do?
The V equals plus 1 minus 1 plus 2 over 400.
Plus, you said plus 2?
Plus 1 in parentheses, minus 1 in parentheses, and plus 2 in parentheses. And then over 400.
Joey, that leaves you with the more challenging one. Are you up for it?
Or, plus 1 times minus 1 times minus 1 over 700.
Good job. Good job.
Oh, you're so smart.
Okay. There are 3 different combinations here. These are the 3.
How do you get the last number?
So you have 2 electrons, right? How far away from each other are they?
They're not that one. Like that number.
Well, that's an electron. So you have the electron on the left. You have the electron on the right. Both of them have -1, right? How far away are they from each other?
700.
Because the left electron is 300 away from the +2, and the right electron is 400. That means they're 700 away.
It's not this one?
Oh, that's the, I'm sorry. That's the +2 in the middle. So I'll use my highlighter here. So what's happening is that this corresponds to the red. This corresponds to the purple. Does that make sense?
Why is it not?
That and this.
Why is it not -1?
There's your -1 right here. So there's your K. I told you use +1 for K, right? The -1 is for that. The +2 is for that. Does that make sense? It's like this one, this is the -1 here. This is the +2 here. You okay?
Yes.
And then this down here, so the blue that's covering the whole thing. So this -1 could be either one of these. This -1 could be either one of these. And the total distance is your 700. Now it says on here, this is a, does it say what this is? Yeah, helium nucleus. The 2, right? So this is describing a helium atom, essentially. How many electrons does a helium atom have? 2 electrons. Are the electrons that are in the helium atom attracted to the nucleus? Class, yes or no?
Yes.
Okay. I have more people in the class, but not very many. That's what keeps them there. Are the 2 electrons repelled by each other, though? Yeah. If we solve these out, I mean, we're not going to solve them. I mean, we could, but we don't need to. V here is going to equal a negative value, right? V here is going to equal a positive value, and V here is going to equal a negative value. Oops. So our electrons are attracted to the nucleus. They're repelled by each other. What's greater, those attractions or that repulsion? The attractions. For several reasons. What's one reason why the electrons are more attracted to the nucleus? They're closer to the nucleus than each other. What's the second reason? The charges. It's a +2, -1 versus -1, -1. So the attraction is greater for two reasons. You have a larger positive charge, as well as the electrons are closer to the nucleus than they are to each other. Everybody all right?
Would electrons like stay the same distance if they're moving around?
Okay, so that's a good question. So far, all we're talking about are these little static pictures with the electron just in one spot. But you're right, they are constantly moving around. They will get closer to each other. They'll get further away from each other. In the end, though, the attraction that they feel from the nucleus is much greater than what the repulsions are between those two electrons. Okay. In an atom, the electrons tend to, they're in constant motion. You're absolutely right about that. But they also tend to move around and yet stay as far away from each other as possible. Not always. There's going to be, they'll bunch up and stuff in places, but it doesn't last very long. We'll talk more about that second semester. Okay? But it's why in middle school, you know, I think probably in the end of the unit for atoms, you talked about the electrons being in a cloud. Yeah? Does that sound familiar? Okay. Questions? You guys good? What's that? A brain break?
Yes.
You get 2 minutes.
Is all of this on the quiz on
2
Friday?
minutes.
Or
What
is this
about
just
2 minutes?
Sure.
Okay, I didn't know if we had just over like.
But here's the thing. Is there anything special that we talked about here? No, we're just talking about that equation, right?
Yeah.
And just making comparisons. That's the key. Can you use that equation to make comparisons? Can you say, if my number is big and it's negative, that's a stronger attraction than my number being small? Those are the things that Simon says. What? No, I'm terrible at that. Nope. 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 Nope.
I think we really should.
It's 250. Okay, yeah. I just, for some reason, I thought it was. I don't know why. Yeah, you're right.
All the training.
You're right.
Simon says no to telephone. Sit up.
All right.
Someone just going to a straddle.
In the last part of your brain break, pull up the document that says Atomic Theory 5 shell model. You got a new set of notes.
Simon says do 2 squats. Get low. Oh, no, that is normal. Let's go. Proper form.
Come on, let's get those notes up. So we get ready.
Sorry.
Next part.
I was a good son.
It's not really.
When we're doing a really good in here, we should have like a class like party with like food.
You just got done with lunch.
No, we didn't.
Oh, yeah,
Like 3 hours ago.
Did you have a lunch?
White.
Yeah.
Oh, okay.
Oh, that's right. How is he?
Okay. So development of shell models. So what we've been doing up to this point, we've been talking about shell models. We've been talking about electrons specific distances away. When we talked about Bohr and the electrons jumping up and down between energy levels and absorbing and releasing energy. Shell model. I think I may have asked you guys this already once, but in middle school, how many electrons, you learned how many electrons can be on the first shell? 2. How many on the second?
8.
And on third? 8, but that's not true. Okay? So, we're going to see how that model got developed based on evidence, based on experiments that are being done. And ionization energy was used. So I think we have a pretty decent idea of what ionization energy is. It's the amount of energy required to remove an electron. But now we got to be a little bit more specific. So the term we're going to use here, or the ionization we're going to use here, is specifics called first ionization energy. And the definition is fairly simple. It's the first ionization energy of an element is the minimum amount of energy required to remove an electron. Now for hydrogen, that's easy. There's only one electron. But say fluorine, for example. Fluorine's got 9 electrons. Look at the periodic table. It's element number 9. So if fluorine has 9 electrons, one of those electrons is going to be easier to remove than all of the others. That would be the first ionization energy. But technically, we could say that fluorine has 9 ionization energies. It's got a first, a second, a third, fourth, fifth, sixth, seventh, eighth, and ninth. Each electron would have its own ionization energy. So we're talking about removing just one single electron. So this table, these are the energies required to remove one electron from an atom. Now, we've switched units, that's okay. In the notes that we've had up to this point, everything's been based around like joules. Now we've got something else now, okay? But the same basic principle applies. The larger the ionization energy, the stronger the attraction that was. So we could look at this list right now and say, which element in this list is going to have the strongest attraction to the electron that's being removed? Looks like helium, right? What element's going to have the weakest attraction for an electron? Yeah, look at potassium. It's got 0.419. Okay. Oops, wrong thing. Crap. Oh. Okay, so Bellman-Michel model. Hydrogen helium. Provide an explanation for why the ionization energy for helium is greater than for hydrogen. And also, why would the values for the ionization being approximately double for helium and than hydrogen be consistent with the idea of electrons in a shell outside the nucleus? Alex.
What was the question?
Why would you expect the ionization energy for helium to be greater than hydrogen? What's the bigger number? +2. So it's got a larger positive charge attracting the electrons. That's it. Now, this ionization energy, basically what it is saying is that in this case, the 1.31 megajoules per mole, that's the ionization energy for this electron right here. So the attraction that's occurring between that electron and that nucleus, it requires the input of 1.31 megajoules to break that. For the helium, same basic idea. So this electron right here is attracted to the nucleus, and it would require 2.37. But the very same value, this electron right here, is attracted to the nucleus and would require 2.37. Even though there are two different electrons, if you remove either one, just remove one of them, it wouldn't matter. They would require the same amount of energy. Because the distance between them and the nucleus is the same. The charge of the nucleus is the same for those two electrons. What I am not saying is if you remove one of them, then the next ionization energy, the second ionization energy, that would become different. Now, provide a possible explanation for why the ionization energy for helium is less than double the ionization energy for hydrogen. Zoe.
So the electron being further away from the nucleus and
So distance, that's what you're saying? Is that a yes?
Yes.
Okay. So distance from the nucleus. you can see there, I've included the radius. So the distance between the nucleus of hydrogen and the electron is 28 picometers, and the distance between the nucleus and the electron in helium is 31 picometers. That distance got a little bit bigger, right? Which means the attraction does what? It gets smaller. J. What's the other reason?
That is part of the, say, you already said the radius is small.
Yeah, so we already taken care of the distance. What's something else about that atom that would make it easier to remove those electrons?
The helium atom,
Yep.
is it because of the two?
Well, okay. So I need to back up because the way I said that is misleading. In helium, we would expect the value to be double. Everybody okay with that? If the distances were the same, correct? Because we've got twice as many protons in helium than we do in hydrogen. Now, it's a little bit bigger, which means the attraction is going to be a little bit smaller, but the 2.37, that's far enough away from being double. So 1.31 times 2 would be 2.62, correct? So that small change in distance isn't explaining why it's not double or why it's so far away from being double. There's something else going on in this atom that would make it easier to remove those electrons. Anything, Jay?
Is it because the first one is full?
Huh, okay. First ring's full. Why do you say that?
Because there's two,
To what?
electrons.
Two electrons. And we, a couple minutes ago, I said, you guys learned it. First ring is only two electrons, right? You're getting closer. It's not because it has two and is full. It's something else. We've talked about it today. About 30 minutes ago. Who else got an idea of what it might be? It is related to charge. Alec? Or not? Zoe?
Is it because there's another electron and they have negative charges?
And do what?
They repel each
They
other.
repel each other. So the repulsion between those two electrons is reducing the attraction to the nucleus. Are those electrons still pretty strongly attracted? Yes. But the repulsion, when you get more electrons in an atom, you are going to get more repulsions. And that's going to reduce the attraction of those electrons for the nucleus itself. In the end, the attraction of the electrons to the nucleus wins. That's why they stay in the atom. But the more electrons you get, the weaker that attraction from the nucleus becomes because of those repulsions. Who's got questions? Okay, we're going to stop here.